So, what I'm going to talk about in the next 2 days is basically a summary of my other course. So I have another course on neuroimaging, and so the plan today is just go over the main points, just the main points. So if you want more detail on this, I teach that course in the fall, where we go over MRI and EEG and MEG and cortical surface methods for reconstructing the brain, all that good stuff. So today I'll talk about two things. So first, we'll just talk about the source of an EEG and or an MEG signal. So what conditions are required in order to be able to see a signal on the scalp? And it turns out it's a little more specific than you might at first think. And so we'll go over what just from the point of view of the actual neurons, cable theory and the individual neurons, why can we see something at the surface? So that's the first thing. And then we'll talk about MRI first, what are the main parts of the MRI machine, and then we'll talk about the Bloch equation. So the good thing about MRI, there's only two equations. There's the Bloch equation and the Fourier transform. And so if you can understand those two, it's literally just two equations, then you can basically understand how MRI works. So this is going over it a little fast, but we'll just sort of try to make it as understandable as possible. So starting off with the source of the EEG and MEG. So EEG and MEG, you put electrodes on the scalp, scratch a little bit to get a good contact, and then you record little currents that are coming out of the brain, through the skull, through the skin, into the electrode. That's one thing you can do. And the other thing you can do is MEG. And MEG is basically recording the magnetic fields that are created by the currents inside the head. Not the ones coming through the scalp, because those are really tiny. You can sort of ignore those. But the ones that are flowing around inside the head. And how does that work? So what's the relationship between current and a magnetic field? And the relationship is the right-hand rule. So if your thumb is the direction of the current, then your fingertips tell you what the direction of the magnetic field is. And so they'll be at right angles to each other. So if the current's flowing in this way, then the magnetic field will sort of, come out and then, back that way. So you can either record, the little tiny currents that come through the scalp, or the magnetic field generated by the currents that are inside the head. And they basically record the same thing, the same phenomenon. It's just two different technologies. It's actually good to use them together. It's kind of a pain in the butt, but it's good to actually put the electrodes on and do MEG, because they give you a non-overlapping information. But what is our point here? So what actually causes a signal to appear at all? And so if I draw like a nice big picture of a little piece of the cortex. So this is supposed to be just a little piece of the cortex. So here's the gray matter, and I just drew one sulcus down there. And then here's a gyrus coming up like that. So this is the white matter down here, and this is the gray matter. So what causes the EEG and MEG? So it turns out in order to get any kind of signal, we need three different things in order to make a visible signal. So that's the cortex, and then there's some layers. There's some dura and other things on top of the on top of the cortex, on top of the gray matter. And there's a little fluid sort of cushion your brain. But then you get the skull. So this is the skull here. And the skull, has pretty high resistance to current flow. And then on top of that, you have the skin, So there's a little fat in there too, but we'll just call that skin, a little layer of fat underneath the skin. And then finally, you get the actual electrode. So there's the electrode, on top of the skin that's recording this EEG signal. So there's an EEG signal. Okay, so what could cause that? So it turns out you need three separate conditions. So the first one you need is oriented dendrites. So what does that mean? So it means you have to have some elongated, sort of anisotropic dendrites. So if you look at like a pyramidal cell has a nice, it's got some dendrites sticking out here, but it's got a nice kind of elongated structure to it, and that kind of setup can give you a signal that you can view at a distance. Now there's other neurons that we'll just sort of draw a cartoon of them. They don't look like this, but if the neuron is sort of more or less has dendrites that go in every which way, every which direction, then it turns out that one is not going to make a signal that's visible at a distance. And so this is, versus. So yes for this one, no for this one. And so why is that? Well, how do neurons work? Remember back in the ancient times when we talked about the membrane and then the cable theory, that's the idea that the membrane is a very good resistor. And so say you have a sodium channel over here, so sodium is positive, and you open the sodium channel, some sodium goes in, it's going to tend to sort of flow down the dendrite. It's not going to tend to flow back out. A little bit will leak out, and so when you get finally down to the cell body, you'll get some of that plus leaking out. Could go out through other channels, for instance, but basically it's going to go a long distance inside the conductive goo that's inside the neuron, and it takes a long time for it to leak out. And so what does that do? Well, you can view the inside of the cell as kind of the void that's not accessible to an electrode unless you poke an electrode inside there. And so what happens macroscopically when you do this to a cell, some plus disappears. Some plus sort of goes into the cell and disappears. And so what does that do? That sort of makes some minus. And so you get some minus in a place where the plus is going into the cell, and then you get some plus down here. So you get some plus at the bottom where the plus is coming back out of the cell. And so that has the potential to give you the separation between these two. So these guys are separated. So the separation between where the positive charges are disappearing, making it appear negative, and where the positive charges are erupting out of the void, making it appear positive, that's what makes a signal visible at a distance. Now, if you have a cell like this, what will happen is, some sodium might go in here. So say there's a channel, so sodium goes in here, and then it sort of leaks out here, or it leaks out here. And the end result is it kind of all cancels out. And so if you have if the dendrites are sticking all out in different directions, and you excite them all, what happens is, at a distance, you can't see anything, no separation. So we just say little separation between in and out. So these kind of cells won't make a signal. And so that's the unfortunate thing about MEG or EEG, is that you only see a proportion. You don't see all the electrical activity going on in the brain. You just see the electrical activity of of cells that are oriented. That's number one. But then number two, they have to be aligned. So not only oriented but aligned, because if these oriented cells are oriented in all different directions, then the same thing is going to happen. They're going to sort of cancel each other out. And so it requires basically that you've got a cell here, and then there's like a cell, right next to it, and that guy's sort of lined up the same way. And there's another one over here. So they have to be all aligned with each other. So that's number two. And that's not true in all different parts of the brain. Some parts of the brain, the amygdala, for instance, there's spiny cells in the amygdala, but the amygdala is kind of, the cells don't tend to have long apical dendrites, and so you're not likely to get a big signal out of the amygdala. But then you still need a third thing. So let's just look at this picture here. So we put some sodium into the top, and then it sort of leaked out the bottom. But what if we had put the sodium in? What if the sodium channel was down at the bottom? So say there was a sodium channel on the basal dendrites. Then what would happen is some sodium would disappear near the cell body, making it negative down here, and then it would kind of erupt out of, it would run down the cable and erupt out of the apical dendrites eventually, and it would appear positive up at the top. So if you stimulate the top of a cell, you'll get sort of negative to positive. If you stimulate the bottom of the cell, you'll get negative at the base of the cell going to positive at the top of the cell, the exact reverse. So if we stimulated sodium channels at the base and at the top, then they would cancel out. So you need a third thing, which is, we'll call it, coherent layer specific activation. So you actually have to activate a particular layer coherently. Many cells have to get their basal dendrites activated, for instance, or many cells have to get their apical dendrites activated. So those are the three things that are necessary to actually to generate a signal that you can see at the surface. Now there's other problems. So say we activated the apical dendrites. So we've got some sort of negative, I'll put it horizontal. So we got some negative action going here, and we got some positive action going here. So if we conventionally say that current goes from negative to positive, so the current flows that way, you can sort of have the current flow either way. There's two conventions. You can sort of, depending on what you think the charge of the thing is, but normally people just say current flows from negative to positive. So if you do that, what's going to happen is we still have to record it, and so it's got to sort of leak out, and eventually sort of get out to, some electrode that's over here, and then there's going to be a little bit of current flowing this way through the skin, and so basically what you'll have is on the surface you'll see some positive, on this electrode. So what do you see on the surface? You see some positive on this electrode and some negative on this electrode. But there's additional complications because the skull is not a very good conductor, and so the current's going to tend to flow. Like, I don't want to go through the skull. I'd rather just flow through this conductive goo, and so the current is going to tend to sort of be deflected by the skull. So that's yet another problem, kind of a higher order problem. But the bottom line that I want you to remember is, what causes the EEG signal to be, what causes an EEG signal that's visible at the surface? And what causes it is you've got to have oriented dendrites. They've got to be aligned with each other, and then they have to be activated in a coherent way, like in a particular layer. Otherwise, they'll cancel out. But if all those things are true, then you can see a signal at the surface for EEG. And MEG, it's pretty much the same thing. So let's take this example here where we've got sort of negative, some positives flowed into the apical dendrites. Let me draw those here. So here's some positive that's going into the apical dendrite, and also this guy, because they're all coherent. So some positive, went into the apical dendrite, and that made some, negative here and some positive here. So how does that relate to MEG? So MEG is the magnetic field created by that current flow. So the current flow is going from negative to positive. So how would you use your thumb and your fingers to indicate that? Well, if your thumb, it's a right-hand rule. So if your thumb is the direction of the current, then your fingertips are the direction of the magnetic field. And so what's going to happen is the magnetic field will come out that way and then go around the back of the cell and come out the other way. And so if you look at that from the surface, so like say here's the surface of the person's head, there's their nose, say, and say we had some current that was flowing that direction. So here's the current flowing. We'll call that guy that's the J vector. So that's the current. So what is the magnetic field going to look like? Well, if you have the current flowing that way, it's going to erupt out there and then go in there. So what does that look like? There's going to be some plus over here, plus magnetic field, because the magnetic field is signed also. So there's going to be some plus here, and there'll be some minus here. Minus magnetic field. So what are these guys? This is the B vector, the magnetic field vector. So if you have a sideways current flow in the cortex, on the surface, if you measure the magnetic field, you're going to get some positive magnetic field on one side of that current flow and some negative on the other side. So that's basically how the MEG works. So and the other difference is the MEG is more expensive. So MEG is like about 20 times more expensive. But it's kind of the same thing. It's recording the same thing. It's just recording oriented dendrites that are aligned, that are coherently activated. Okay, so that was EEG and MEG. That's it. So any questions about EEG and MEG? What causes it? So it's not all the currents flowing. It's just the ones that have this property. But it turns out, a lot of the cells in the cortex have that property. Some cells down in the brainstem have that property. Like, for instance, if you go down to the equivalent of nucleus laminaris, those guys are all lined up in nucleus laminaris, and you can see a signal from some of those auditory structures down in the brainstem. Okay, so much for MEG, EEG. So let's head over to MRI. So how does MRI work? So this is how you get the signal from MEG. So now what we want to do is try to figure out where the signal comes that you record in MRI. And so we'll first... Oh, one last thing. Sorry, just back up to this one last time. which is relevant. Say you put an electrode down into the cortex. So, what does an electrode look like? It might have a sharp point, and then there's some insulator on it like that. So this guy's an insulator. And say you've got maybe, it's a 10 microns, that's 1/100th of a millimeter, of the tip exposed, something like that. That's a typical electrode. So if you put that electrode into the cortex, you'll actually be able to record spikes. But interestingly, if you put that electrode into the white matter, you don't hear anything at all. And why is that? Because there's zillions of spikes coming, there's the axons. White matter is just total axons, so all it is just spikes going every which way. But this electrode can't pick it up. And the reason it can't pick it up is because the currents, the return currents are all sort of canceling each other out on the axons, whereas these guys are not canceling each other out because they've got this big separation between where the current is going in and where the current is coming out. So it turns out, it's just an empirical observation. You put an electrode in, you hear all these action potentials as you go through the cells, and you go down into the white matter, nothing. It's completely quiet. You'd have to use a teeny tiny pipette. So if you make a little pipette with a tiny little opening, the opening is like only, say, 1 micron across. If you put something like that down in, then you can actually start to hear the spikes that are in the white matter. But the standard electrode, sharp electrode with an exposed tip that's about the size of a cell body, you can't hear anything. So, but what you're seeing there is pretty much the same thing I talked about here, is that you've got these cells that are elongated, and there's a separation between sort of where the charges are going in and the charges are going out, and that's an electrode like that can pick it up. Okay, sorry for that backup, but that was just sort of a practical thing if you're trying to record from a neuron. Okay, so I didn't bring my notes, so we'll have to do this by ear. Okay, very good. Okay, so let's look at the magnet. So here's the magnet. Just make sure I don't have any. Nope. Okay, we'll do this entirely by ear. So here's the magnet. So the magnet has these superconducting coils in it. And these superconducting, they're little bundles. There's like 4 little bundles in there. And they have a huge amount of current in them. But the amazing thing is they're not plugged in. Like, you just put the current in there and then it just goes around by itself. And so if that current is, say, moving in this direction, then that's going to make a magnetic field in this direction. So this is, put it over here. So this is that's the J, that's the current flow. And then this guy is the B, that's the magnetic field direction, the positive magnetic field direction. And so that thing is called the B0 field. That thing is called the B0 field. And so what does that do? So many years ago, people did this very simple experiment where they took a really strong magnet like this. It's a really strong magnet. And they shot a beam of atoms through it. So if you shoot a beam of atoms through it, and when it gets to where the magnet is, the atoms they're like little magnets, and they get polarized. And when they get polarized, they fly off into 2 separate beams. Now, that was kind of surprising to people because they figure, they would come in at all different angles, and if they came in at all different angles, then they should react to all different angles to the magnetic field. But instead, they just separated into 2 beams. And that's the purpose that's the purpose of this B0 field. It's to slightly magnetize you, slightly polarize you. And so it will essentially polarize a small number of the magnets that are in your body to be lined up with the magnetic field. So it's kind of, so at the quantum mechanical level, you do a measurement. This is like a quantum mechanical measurement, but in some respects, what we're doing in MRI is like a continuous measurement, because we've stuck you in there and you're just continuously polarized. But if you're just continuously polarized, you won't make any signal. You'll be slightly magnetic, tiny bit magnetic. You're not a very good magnet. You're only polarizing like 1 in 10,000 or 1 in 100,000 atoms. So it's a very small number that are lined up, that their little magnetic fields are lined up. So that doesn't do anything. It doesn't make any signal. And so to make a signal, we have to somehow deposit some energy into these protons. And to do that, we have another coil in there. So there's a coil in there. And this one is called the body RF coil. It's kind of what forms the Bohr, actually. So let's number these. So this is the B0 field is number 1, and then number 2 is the body transmit coil. So body transmit. So that coil generates a magnetic. It's also a magnetic field that generates a magnetic field that's rotating around like that, perpendicular to this other field. And so that one is called the B1 field. So that guy's a rotating one. So it's rotating. And the frequency of it is like an FM radio, like FM, 98.1. Our frequency is about 123, so it's very similar to the frequency of an FM radio. And what that does is that sort of gets these polarized protons and kind of sweeps them all into alignment with each other, so that for just a short period of time, they make a little radio wave signal, little electromagnetic signal that comes out of your head. And so we essentially add this magnetic field. So this B1 field is just added on to the B0 field. So what does that mean? So the B1 field, B0 field is really, really big, and you add a small rotating field onto it, and that just causes the sum of them to sort of wiggle around like that. And so that's this body transmit RF coil. That means radio frequency coil. So then you've got your head in there. So let's draw the person's head in there. There's a head. So you got the head in there. And then we've got some coils that are around your head to pick up the signal. So here's some coils around your head. And so that's number 3. And that's the RF receive coils. And so those pick up this small signal that comes out of your head. So RF receive coils. It only comes out for a little bit of time, like about 1/10 of a second or so. So you have to record pretty quickly. So the last but not least, we've got another thing in there, which is the gradient coils. So this is the basic source of the signal. You go in there, you get magnetized / polarized. Then you do a little pulse through the body transmit coil that sweeps everybody into alignment with each other temporarily. because those little magnets are rotating, they'll generate a current in the coil, and then you get a little oscillating signal that comes out of the coil, and that's your basic signal. And then we modify that by messing with the gradients. And so there's yet another set of coils in here, and these are the ones that make noise. So if you wondered what actually makes, none of the stuff that I've talked about so far makes any noise. So these guys make noise. And so what are those? Those are the gradient coils. So number 4, gradient coils. So those guys mess with the magnetic field. So what do? They mess with the B0 field. They just attempt to only affect the B0 field. And there's 3 of them. And so what you can do is you can, affect B0 field. And what is the B0 field? The B0 field equals the BZ field, because here's our coordinate system, so that's the Z direction. And this guy is the Y direction, and this guy coming out at you. So this is Y, X, and Z. So they just affect the BZ. And there's 3 of them, so you can affect the BZ when you move in the X direction. So like affect Z, moving in X direction. That would be like left, right. Or, moving in the Y direction or moving in the Z direction. So there's 3 different ones. But they always just affect the Z component. So if you turn on like the X gradient, which is left to right, it will make the B0 equals the BZ just a little bit bigger on one side of your body than it is on the other side of the body. That's what the gradients do. Because they make magnetic fields, they interact with the main magnetic field, and it causes noise. So that's where all the noise comes from. Okay, so that's the parts of the magnet. So now we need to talk about the Bloch equation, and like I said, there's only 2 equations. So there's just the Bloch equation and the Fourier transform. And then you understand all of MRI. So today we'll do the Bloch equation. So the Bloch equation, it's a vector differential equation, I always say, which doesn't sound too hopeful, but it's actually it's got 3 parts. So we'll talk about the 3 parts of the Bloch equation. And it's not a quantum mechanical equation, actually. So you don't need quantum mechanics to understand it. It's a classical equation. So the Bloch equation. So the Bloch equation is a vector differential equation. And so what it does is it explains how the magnetization in a little piece of the brain is going to change over time. And so that's our M vector. So, and dt, that derivative just means, so what is that in words? It just means, how does what direction, because this thing is a vector, what direction does local mag field change in for small bit of time? So that's the meaning of that. So for a very small bit of time, how does the local magnetization in some part of your brain change? So that's the first thing. And so we got there's three pieces that are going to affect that, the change in the magnetic field. And it turns out these three pieces are all perpendicular to each other. So here's the first one. So the first one is the one that explains this movement that's like a top. Like if you have a spinning top or a gyroscope or something like that, if you spin a weight around an axis, what happens is if you put it on the ground, it will sort of tend to sort of like, it's spinning rapidly around its axis, but it will tend to sort of like go around in a little cone shape. So that's what this first term explains. And it's the cross product of these two things. So that M is the same as this M. So that's the same that's the same M. That M is the same. But this M says, like, how is the M going to change? This is like the whole length of the M as it currently is. And then there's a B. That's another variable. This guy's a constant. This guy's a constant. The gyromagnetic ratio, we don't have to worry about that too much. It's a fixed number. But then there's the cross product. Yeah, so what's the cross product? So let's just draw these two out. So the first one is the B field. And so what's the B field? Well, the B field is pretty much anything that affects the magnetic field. So this includes the B0 field from those superconducting coils, and it includes, the RF transmit field, because you might have turned that on, and that's another magnetic field, very rapidly changing one. And then the gradients also. You might have turned the gradients on, and the gradients might affect the B0 field. So everything's in there. They all just add to each other. They vector add to each other, and you just get one arrow. And that one arrow is basically the sum of the effect of the B0 field plus whatever the radio wave is rapidly oscillating around radio waves at a particular instant in time. That would be the RF transmit contribution, and then you add the gradient onto it as well, whatever the gradient happened to be at that point in time. And so it's just, you just end up with one arrow. So let's draw that arrow. So they conventionally, even though it's horizontal in real life, they conventionally draw this sort of up like this. This guy is the B, not B0, it's just B, because it's got everything added to it. Because it might have wiggled a little bit from the RF transmit, and then the gradient might have shrunk it or expanded it a little bit. That's the B. And then we've got another vector, and this is whatever the local magnetization is. So this other guy is local magnetization in small piece of brain, of sample, also known as the brain. So we got some magnetization there. And so what this equation says, if we just look at this, it says the vector that is the change in how this M vector is going to change over the next small time point equals whatever the M vector currently is, cross-producted with the B vector. So now we have to do the cross product. And if you take my other class, we'll go through the cross product in detail, but the cross product is going to be a vector. It's going to be another vector that's perpendicular to these two. So what does that mean? So there's going to be a vector, sticking out this way, and that vector is going to be, perpendicular to this guy, but also perpendicular to that guy. So these two vectors, the m and the b vector, that defines a plane. And so this vector down here, this guy is the dm dt vector, is going to be perpendicular to both of those guys. And then what does this tell us? It tells us how is this M magnetic field going to change in a small fragment of time? And so that means, how does it change means we have to add it to the M vector. And so we take this guy and paste it up here. So let's paste it up here. So it's dotted. He goes up here. You paste him up here. And that one says, okay, so for the next time point, if we add that little vector onto the big one, the big M vector, then we get our next time point. So here's our next time point of the M vector. So this guy, this guy was the M vector at time t, and then this guy is, the M vector at time t plus 1. Okay, so now this is the differential equation, so you can sort of get the idea of a differential equation. So now we have to do it again. And so what happens when we do it again? Well, this new M vector has moved a little bit. Because, we added this little dm dt on top of it. So here's our M. So now that's going to make the plane between the b vector and the new M vector slightly different. It's going to rotate the plane a little bit. It'll sort of, you can see how it's going to rotate it from where it was. And so we calculate again, and we'll get another slightly different dm dt vector. And if you just do that, what happens, you can see it's going to go around like this. Here it's coming out of the plane there. So what will happen is this this equation, if you keep operating it, will cause this precession motion. And that precession motion will just go on forever if nothing else happened. So if this is all there was to the Bloch equation, it would just keep going around like a top without any friction. So now we have to sort of add the friction. And so the first friction we add is the T2 decay. And so now we have to break the M vector up into its components. And so if you imagine you've got like an M vector over here, what we can do is we can sort of break that M vector up into its three components. So you have like if we call this, call that guy the Y, and this guy the X, and this guy the Z. So, here's the X component, so that's the MX. And then this guy would be the MY, and this guy would be the MZ. So if we just sort of divide this original M, so here's the original M vector, into its perpendicular components, because we need to just consider the X and Y part, then we have the MX times, we'll make it into a vector by multiplying it by the unit vector in the X direction. That's what this is. Unit vector X. So that means like a vector of length 1 in the X direction, times a number, which is how big it is, like say 2. So 2 times 1 is 2. And then we add to that the vector in the y direction. So basically what we want to do is we just want to get the xy component of this. And so what is that over here? That's basically this vector here. So this guy is the mx times the unit vector in the x direction plus my times the unit vector. The j stands for the unit vector in the y direction. And so this guy is, if we just decompose this m vector into the xy part of it and the z part of it. So this thing over here would be, the mz times ijk, the unit vector in the z direction. So all we did was we just sort of broke up the m vector into the xy part and the z part. That's the whole point of all that mess up there. So now we divide that by T2. And so now if you've ever heard of MRI, you know about T2. So T2 decay. So all this says is find out how big the x and y component of the m vector are put together, and then divide it by T2, and then subtract it off of this thing. And so that's going to cause the m vector to since it's subtracted off, it's going to cause it to get closer to the center. So let's just draw a much bigger picture of that down here. So here's our, so I can draw the separate vectors. So here's our b vector, and then here's the m vector just coming up. I'm drawing these things bigger than they are so we can sort of see them. So this guy is the m, and this guy is the b. And here's the direction these guys are going around. So we already had one additional vector. That was the part that came from this first part that's causing it to sort of go around the circle. And now we've got a second one right here, and this second one says let's subtract a little bit of the xy component off. So here's where the vector comes through it comes through. So let's subtract a little bit of that xy component off. So here's the whole xy component, and we're going negative, so that means going in the opposite direction of the way it's pointing here, but just a little bit. And so it's going to subtract a little bit off, aiming toward the center. So that's T2 decay. So basically, this guy here is doing this part, and then this guy here is doing that part. So it's making the vector, it's making the m vector get a little closer to the center. That's T2 decay. And when you look at this, you might wonder, like, why is the T2 underneath? Because T2 is a time constant. And so why are time constants always divided? Why you're always dividing by a time constant? Well, just think about it. If the time constant is large, like 100 milliseconds, that would be large. So if that number is a large, you're dividing by a large number. And when you divide by a large number, you get a small thing. And so the amount of decay is small. So a long time constant, a large time constant, because it's in the denominator, makes the amount you're subtracting small. And so that means it will take a long time to decay because you're not subtracting very much. Whereas if you have a small time constant, if you put a small number in the denominator, you'll get a bigger number for this whole thing. And so then the decay will be more rapid. So that's why time constants are always underneath. Okay, so we're almost done. We got one more decay. And so the one more decay is m. So the mx minus mz0. So that's one more constant. So this guy is a constant. So this is a constant, and it's called the equilibrium magnetization. And it turns out if you go in the magnet, there's a certain amount you can get magnetized. And it's strictly related to basically just how many protons you have there. So that's extremely simple. Just total number of protons tells you how much you're going to get magnetized at a given magnetic field. So that's a constant. It just depends like how many protons are there in this particular chunk of brain. So, and then mx is whatever the current, it's this guy, mz. Sorry, that's supposed to be mz. You're supposed to yell at me. Okay, so mz is whatever the current z component is, and that whole thing is multiplied by the unit vector in the z direction and divided by the T1 constant. So that's how T1 gets in there. So if you've heard about MRI, you have proton density, which is basically how many protons you got, and you've got T1 and you've got T2. So everything's all there. So this thing, how does this one work? Well, this one's kind of a little backwards because mz is the maximum magnetization that you can get. And mz could basically just be smaller than that. And so this number is going to be a negative number because mz is like the maximum that you get up to after you've been in there for a couple seconds. And so mz at any point in time is going to be less than that. So that's a negative number. And then we make a negative of a negative, that makes a positive number. So that one's going to actually be a positive. It's going to be move you in this direction. It's slower movement. I drew it big there so we could sort of see it clearly. And so that one is going to basically make this b vector longer, the m vector longer. And so when we add those, they're all perpendicular to each other. So this, that guy's perpendicular to that guy, and that guy's perpendicular to that guy, and that guy's perpendicular to that guy. All perpendicular to each other. And when we add them all up, then we get our new m vector. So here's our new, I'll just slightly bend it around the corner so I don't get rid of the arrowheads. There we go. So there's that's our new m vector. M new. So m vector new. So that's the Bloch equation. So there you have it. That pretty much explains everything about how the contrast in MRI works. And what is, I didn't explain how we sort of, figured out the solution to the equation. So this is an equation that just tells how things operate over a small period of time. But what we really want is the solutions to Bloch equation. And what we can do is we can separately solve for the different parts. So we could solve for this. What's the solution if we just got rid of this part of the Bloch equation and just considered the precession? How do you end up at this circle business? That's the solution. The Bloch equation just tells you like what's going to happen over a fragment of time, but it doesn't give you the whole picture of like what happens over like 5 seconds. That's what the solution is. So we could solve for this guy, or we could just solve for this guy. So let's just look at what's the solution when you solve for the T2 part of the Bloch equation. And what the solution looks like is you start off at some amount of X and Y magnetization, and then you fall off quickly over time. So that's time like that. So that's the solution. So this is solution for T2. And it's pretty quick, like this might be, say, 50 milliseconds. Depends on the field strength, but a tenth of a second, 20th of a second, it's pretty much gone away. If we look at the T1 solution, because the T1 time constant is different than the T2 time constant, it's a much longer time constant, bigger. Like, for example, 1 second. This is like, for example, 50 milliseconds. So because that time constant is longer, what's going to happen is if you solve for the T1, it's going to go up, really, it'll eventually make it all the way back up to the MZ0. So here's the MZ0. So there you have it. That's pretty much, but I didn't tell you the most important thing. Why do we do this? Well, we do this because we want to see contrast between different tissues. And so what we're really interested in is, what if you've got a different tissue and it has a shorter T2? So this is, this is one T2 tissue. And then this guy is another contrasting T2 tissue. So a different type of tissue might have a different T2. And you could see the same thing for T1. So maybe we've got another tissue type, and that tissue type recovers a little quicker. It gets up to the same place, but if it recovers a little quicker, so this is, one T1, and then here's another T1. So like white matter recovers a little quicker. So another T1. So, for example, white matter, that recovers a little quicker. Gray matter takes a little longer to recover. So that's the whole point of MRI. We're trying to get like a contrast, between two different tissues. So then we have to end up sort of like considering two different tissue types, and how do we set things up to get a contrast? So this is contrast. That's actually what we're interested in. So that's T1 contrast. So you can have T2 contrast or T1 contrast. But the basis of the signal is not, it looks kind of horrible at the beginning, but there's not too much to it. It just says, here's how the magnetic field in the brain is going to change over a small period of time. You got one component, which is the thing that causes this precession business. You got another one that's shrinking you toward the z-axis. That's the T2 decay. And you got a third one that's growing you toward the this equilibrium, constant equilibrium magnetization. Yeah, sorry, I forgot to put equilibrium magnetization. You have another one, that's this third one right here that's growing you in the z direction. And so that pretty much explains, it's just a classical equation that explains pretty much how the magnetization changes over time. It's got everything in it: proton density, precession, T1, T2, pretty much everything. So it's kind of complicated, but it's only one. There's only one equation. So then there's all there is the Fourier transform. Just the Fourier transform. We'll do that next time. So okay. So questions about this? About what makes the signal? So this is what makes the signal, those precessing protons, and that's done by the RF coil. And then this Bloch equation explains like how that signal changes over time. All parts of it. And then you got T1, and that's where T1 and T2 comes from. Okay. Yeah, I probably did it better without my notes. So I think it was clearer. So, any questions about this? So first time through is always rough, but it's just the positive thing, like I say, is it's just one equation. It's got everything in it, because you probably have heard of T1 and T2 if you've done any or had any involvement with MRI. Okie doke. Any last questions? Yeah, I mean, I think it's, for me, you know, not being a mathematician, for me it's important, the actual geometrical picture is the most important, just sort of seeing this, you know, the actual sort of physical geometrical picture. Okay, well, we'll head to the Fourier transform next time. This Fourier transform is very useful for a lot of different things. You might want to use it for a whole bunch of different things you're doing. So we'll go over that one and try to explain how you get an image, because this just said like you got a chunk of stuff in there. It doesn't say how you actually sort of like make an actual 2D or 3D image out of it. Okay, David, I think we're done.